In this video, we're going to survey the 3, 4, and 5 carbon aldoses and ketoses. And I wanted to start the video by explaining a little bit about why we're doing this from a perspective of organic chemistry and fundamental biochemistry. Number one, we are not doing this to memorize the structures of these sugars. As far as I'm concerned, there is no need to memorize the structure of any particular sugar, the one exception perhaps being glyceraldehyde, which is important enough and small enough as a triose to keep in mind. It's also helpful for recalling the difference between D and L for sugars. But for all these other sugars, there's no reason to know any particular sugar's relative configuration, right? There's no reason to know the configurations associated with the name mannose, for example. The main reason we're doing this is to point out some interesting stereochemical relationships between the different types of sugars and to sort of compare and contrast their structures. We're going to see that there's some interesting stereochemical implications that come out of this. For example, there are 4 pentoses. There are 2 tetroses. There are very good stereochemical reasons for this based on the number of stereocenters in each sugar. We'll also compare and contrast the aldoses and the ketoses in structure and see how these can differ. A big general point to make is that all of these sugars, with all their different names, have very different properties. Differently named sugars are diastereomers of one another, assuming they have the same number of carbons. So these sugars in the same class that are named differently, we should expect to be diastereomeric and have very different properties. For example, xylose is going to have very different properties from arabinose, for example, in general. Now, generally speaking, monosaccharides are solids due to the large extent of hydrogen bonding. They're often soluble in water because of the large number of hydroxyl groups. So their properties aren't hugely different, but we should expect noticeable and measurable differences in properties between these different sugars and chemical reactivity as well. Interesting things can happen due to these differences in configuration with respect to chemical reactivity. Okay, with that prelude out of the way, let's start surveying the aldoses. And these are sugars, monosaccharides, that contain an aldehyde functional group in their open chain form. The open chain form is typically drawn as a Fischer projection with the aldehyde carbon, carbon number 1, at the top. The 3-carbon aldose, the aldotriose, is glyceraldehyde, and we looked at that on the last slide. This is kind of the parent aldose, the smallest and one that we can build off of to make the larger sugars. The 4-carbon sugars that contain aldehydes are known as aldotetroses, and there are 2 diastereomeric aldotetroses. They are called erythros, in which the OH groups point the same way, and threose, in which the OH groups point in opposite ways in the Fischer projection, and each of those is individually chiral and has an enantiomer. So D-erythros, for example, with this OH pointed to the right at the bottommost stereocenter, which is carbon 3 in an aldotetros, has an enantiomer, L-erythros, with the opposite configuration there and the opposite configuration at the other stereocenter. So these are enantiomers. An important thing to note about erythros in particular is it's actually chiral. You may be tempted to notice, for example, a plane of symmetry right here, but notice the CH2OH group is not the same as the aldehyde group. So D-erythros is chiral, as is D-threose. All right, we add one more carbon, we get to the aldopentoses. And there are now 4 diastereomeric aldopentoses based on the 4 different ways we can arrange those 3 stereocenters in the pentose, the aldopentose chain. We've got ribose, we've got xylose, we've got lixose, and we've got arabinose, and these are all diastereomers of each other. Each pair that we could generate here forms a diastereomeric pair, but each of these is individually chiral, and so, for example, D-ribose has an enantiomer, which is L-ribose. D-lixose has D-xylose, has L-xylose. So each of these has an enantiomer, and we use D and L to distinguish between those. So notice there are 8 ways overall to arrange the configurations of the 3 stereocenters in the chain, but 4 of the ways are enantiomeric with 4 of the other ways, and so we end up with 4 enantiomeric pairs, if you like, or 2 sets of diastereomers with 4 diastereomers in each for the aldopentoses. There are now 8 diastereomeric aldohexoses. So here again, in the aldohexoses, we've got 4 stereocenters, carbons 2, 3, 4, and 5. And there are now 16 different ways to arrange the configurations of these 4 stereocenters, 2 to the 4th power. But 8 of those are enantiomeric with the other 8. So now we've got 8 enantiomeric pairs, if you like, or 2 sets of diastereomers with 8 diastereomers in each set. And because of limitations in the size of my slides, I've just shown one enantiomeric set, just the set of D sugars. Here the L sugars are the mirror images of these with all the opposite configurations. For example, L-allose has all the hydroxyl groups over here and all of the hydrogens over here in its Fischer projection. So it's a good exercise to pause and draw the L sugars that correspond to these, but these are the 8 possible D aldohexoses. And notice they are all D sugars, with that bottommost stereocenter having a hydroxyl group that points to the right in all cases. And the most important of these, and the one that I might say might, if you are so inclined, if these structures capture your attention, captivate your curiosity, the one that might be worth committing to memory is D-glucose. This idea of the right, left, right, right structural pattern and the open chain or Fischer projection form for D-glucose may be worth committing to memory. But there are other ways to remember this, and when we get into the cyclic structures of sugars, it will become very, very apparent why D-glucose is freaking everywhere. There's a very good reason for this, and it has to do with this alternating arrangement of the hydroxyl groups here. More on that later, but this is the one sugar that might be worth committing to memory for your future courses. For my purposes, it's not necessary. The ketoses contain a ketone functional group, typically at carbon 2. There are ketoses with longer chains with the carbonyl group at, for example, carbon 3 in a pentose, or what would be called a pentulose. But those are less important because they're less biochemically relevant, because it's actually kind of hard to get a carbonyl group in that 3 position, starting from the more ubiquitous aldoses, which are everywhere in nature. And so we typically see the carbonyl group at carbon 2, and those are the only structures we're going to look at on this slide. Kind of the parent ketose, sort of analogous to glyceraldehyde, the 3-carbon ketose, is actually dihydroxyacetone. Acetone would have 2 CH3 groups on the ends with the carbonyl group in the middle, but if you throw a hydroxyl group on each end, well, now we're at a carbohydrate, and the chemical formula confirms that. And this is dihydroxyacetone then, or 1,3-dihydroxy-2-propanone, if you like. If we add one more carbon, now we're at the ketotetroses, and there are 2 enantiomeric ketotetroses because there's only one stereocenter now in the ketotetrose structure. And so these can differ in configuration at that stereocenter, and we end up with D-erythrulose and L-erythrulose as the 2 possible ketotetroses. In the ketopentoses, well, now we have 2 stereocenters, 4 possible stereoisomers, 2 sets of diastereomeric pairs, D-ribulose and D-xylulose, and the corresponding L enantiomers of those here underlined in orange. Now with the ketohexoses, well, now we've got 3 stereocenters, carbons 3, 4, and 5. We've got 2 to the 3rd power, or 8 ways to arrange those configurations, so 8 stereoisomers. We've got 4 diastereomers and an enantiomeric set of those 4 diastereomers, and the D set is shown right here. We've got D-fructose, unquestionably the most important ketose, D-sorbose, D-tagatose, here hiding in the right, and D-tagatose, here hiding in the right, and D-psychose here. So I haven't drawn the 4 enantiomeric versions of these, but this is a good exercise to do on your own. Draw the 4 enantiomers of these ketohexose sugars at the bottom of the slide. To close this video, I just want to reiterate that it's definitely not worth knowing any of these sugars in particular. What you should be able to do, though, is recognize isomeric relationships between a given pair of sugars and be able to assign D and L given the Fischer projection. When we talk about cyclic sugars, you'll start seeing other ways to draw sugars in 3 dimensions, things like chair forms and Haworth projections. And there too, it's going to be important to recognize D versus L and another important stereochemical relationship, alpha beta, that we'll talk about later. But the purpose of this video really was just to give you a sense of the stereochemical diversity and structural diversity built into the sugars. There are many different ways we can arrange those hydroxyl groups with a given carbon chain length, right, and still get a carbohydrate. And so there are a very, very large number of diastereomeric sugars that you may come across in your future biochemical studies. They're all fundamentally, though, polyhydroxylated ketones or aldehydes. And so the basic chemistry is going to draw on what we already know about alcohols, ketones, and aldehydes. And we're going to dig into that next as we start to look at some of the fundamental reactivity of sugars, starting with the reactivity they have with themselves, the possibility for intramolecular reactivity of the sugars.